even with maximal mitigation, climate change will occur. In fact, climate change is occurring, and adaptation will therefore be necessary. Now, it's important to make the point that although these are complementary responses, they're going to have to take place at different levels. Essentially, mitigation is a matter for global international agreements. There is a major externality with mitigation that reductions in CO2 emissions in Australia, because CO2 is mixed entirely through the atmosphere in a fairly short period, they benefit everybody in the world. And therefore, there's a substantial free rider problem, which we're still trying to resolve through the Kyoto process and the negotiations that succeeded. By contrast, adaptation is a response that we take as individuals, to a significant extent responding optimally in the light of the knowledge available to us to the changes in conditions that we face. That doesn't mean there isn't a big role for policy here, but it's certainly a very different role for policy than in the case of mitigation. So I want to talk now about the Murray-Darling Basin. Of course, as we know, it's a system already under stress. Even before the most recent severe drought, that was clearly apparent. And whether you regard the current drought as the first manifestation of climate change in the general form of anthropogenic global warming, or possibly a decades-long shift in climate away from the rainfall patterns of the last half of last century, or perhaps just a run of very dry years, whichever of those views you take, it's clear that the stress on the system is now becoming extreme, and I'm sure Mike Young and others will have plenty to say about this in the context of the panel discussion. Of course, we're already seeing through recent events vulnerability to climate change, that we've made a large number of investments in the basin based on the assumption that the climate is more or less going to continue in a stable fashion, based on, to some extent, on the last 100 years of experience, to a large extent on the more favourable experience of the 50 years or so beginning in 1950. So it's very clear that at every level, this is a system that's vulnerable to climate change. Obviously, in raw terms, in terms of flows in the system, but also in terms of ecological adaptation and of the capacity of our social and economic institutions to handle climate change, something which in this context they haven't been doing very well as yet, but have hopes that we'll see the beginnings of an improved approach in the next few years. So, a picture of the basin. I always like to include Queensland in the pictures of the Murray-Darling Basin, a lot of the time reflecting, I guess, the historical development of policy institutions. The basin's cut off, covering only the three original signatory states to the River Murray Agreement, but of course Queensland and the ACT are also included. So it's certainly a very large area, of course, responsible for a large share of total Australian agricultural output and the great majority of irrigated agricultural output. So the main work that I've been doing with the Federation Fellowship, with my team in the Risk and Sustainable Management Group for the last few years, has been to develop and try and improve a state contingent simulation model of the Murray-Darling Basin, the Risk and Sustainable Management Group model. So this model covers the entire basin, and the aim is to model constrained optimisation of the use of land and water, taking account of salinity. The constraints we model are those, some imposed by physical capacity for adjustment and some imposed by alternative institutional arrangements, different systems of property rights, systems that allow trade between regions and systems that don't, and so forth. The model has 18 regions corresponding to catchment management areas, as well as, I'm pleased to say, Adelaide is included as a consumer of water from the basin, and we model and take account of environmental flows, modelled by the amount of water that actually reaches the end of the river. We have a range of production activities in the model, 13 of them. There aren't actually 13 separate commodities. We look at different technologies to produce various sets of commodities. The idea being that we want to model both the capacity to use less water-intensive technologies in response to rising prices of water, and more flexible technologies in response to increasing frequency of drought. So, as we know, some commodities, particularly horticultural commodities, require a steady annual flow of water. Others can be produced on an opportunity cropping basis. And if, as some of our predictions suggest, we're going to see more frequent droughts, that is less reliable water supplies, then we'll see both a shift towards less water-intensive production, but also a shift towards technologies that enable us to make production decisions after we have a better idea of how much water is going to be available in a given season. And so in this context, I've always thought it's a mistake to demonise particular crops, as has been done to some extent in the debate here. We see that some of the crops that are most commonly criticised, like rice, have the merit that we can make the planting decision on an opportunity basis, and that point's been made again by Mike Young in recent discussion, and it comes out very clearly out of the structure of the model we've been working with, which has 3 different states of nature, and those correspond to wet, normal and drought years, and it really turns out that the frequency of drought drives a lot of the results concerning the impacts of climate change. So it's the case that the model can reasonably well handle a reduction in inflows if that reduction is more or less uniform across the board. If wet years get a little less wet, normal years a little drier, droughts a little worse, but the relative frequency of those states doesn't change, then it's possible to adapt to that at relatively modest cost. We need much more substantial adaptation if the climate change takes the form of increased frequency of drought, and unfortunately that's what both the models and our recent experience are telling us seems to be likely, that we won't simply have a steady reduction in inflows, rather we'll experience long periods of drought. Of course, that's in some sense the optimistic scenario. We also have the possibility that the current drought conditions are just going to continue, which would be truly disastrous. So we have a range of climate change scenarios. I'm going to focus on what we call mid-range scenarios. All of the scenarios show that given an increase in CO2 concentrations, we're going to see rising temperature, and from the point of view of irrigated agriculture, that also means rising evaporation. CO2 levels, which have some positive effects on yield, will also tend to increase evapotranspiration. So all of those temperature and CO2 effects are more or less locked in. What we're much less certain about is the change in precipitation that will arise with climate change, the change in snowfall and rainfall. The general PAR prediction is that those are going to decline and that we're going to see more frequent droughts. And those two things translate into a reduction in inflows, quite a substantial one, because inflows to the river system are, of course, a residual after rainfall's been absorbed by plants, absorbed into the soil, into the water table, and in the context of agricultural areas, captured and diverted into things like farm dams. So the evidence we have suggests something like an elasticity of 3, that is a 10% reduction in precipitation could lead to a 30% reduction in inflows, and there's also a more or less one-for-one effect of evaporation, that evaporation will, 10% increase in evaporation will reduce inflows correspondingly. So that's the, as it were, the